Myself, Avinash Prakash, Professor Digital Traction, IRMI. Welcome to this video on ALCO Locomotive Power Pack. Before we discuss different components of power pack of ALCO engine, let's discuss two things beforehand. Brief history of diesel locomotive in Indian Railways, just for introduction, and second thing, basics of diesel engine working in this video. Friends, as we all know, Indian Railways commenced with steam traction in 1853, wherein three steam locomotives hauled the first train service. Due to development of diesel locomotives which had better efficiencies, speed, lesser maintenance requirements, the steam traction was discouraged and diesel locomotives were put into service. Post independence, after Indian Railways decided to shift from steam to diesel traction, we started looking out for modern diesel locomotives perfect for Indian conditions. There were two major companies, American Locomotive Company, that was ALCO, and General Motors. So ALCO and GM locos were shortlisted, and finally the ALCO was selected because ALCO agreed for technology transfer. So these locomotives could now be owned by Indian Railways and could be made as per our conditions. Once we will get the technology, we can make locomotives ourselves. So India entered into technical agreement with American Locomotive Company of United States, and a diesel locomotive manufacturing unit was established at Varanasi in Uttar Pradesh. In the beginning, imported ALCO US loco WDM1 was introduced around 1957, which were having had 12 cylinders, 4-stroke engines and power rating with 1900 HP. The loco was perfect for Indian conditions, rugged, very reliable, powerful enough and had simple construction and mechanism and was very easy to operate and maintain and was very malleable, enabling engineers to tweak and tinker with the engine to produce different versions of it. We also purchased some geo-made locomotive 2600 HP WDM4, but it lost out to the ALCO despite being technically superior and faster. That is, although it was technically superior, but since GM was not agreed for transfer of technology, so it lost battle to ALCO and we adopted ALCO. So it was the ALCO who succeeded, and 2600 HP WDM2 16-cylinder engine diesel locomotives were introduced on Indian Railways in early 1960s with the transfer of technology from American Locomotive Company USA. So we had gone for various upgradation of locomotives. We will see in next slide. When we got the transfer of technology from EMD of GM in 1960, around 1996, in late 90s, there was a shift in planning of utilization of diesel locomotive. We had gone for now GM locomotives, and by that time the ALCO manufacturing of ALCO locomotive was put on hold. So let's see the different versions of ALCO locomotive. Here this is WDM1 locomotive that initially came to our system. This is WDM1. With WDM2 was manufactured in diesel locomotive works Varanasi. Then after a long gap, The operating of the engine was carried out and from 2600 HP to 3100 HP, that is WDM3A and WDG3A, was manufactured in 90s after a big gap of around 25 to 30 years. We had been using this 2600 HP locomotive for a very long time, and hence all the diesel sets have mastered the maintenance of ALCO locomotives at components level on its own without help of any private or AMC agency. So the ALCO company, which became bankrupt in its own country, United States, in 1969, but its supplied loco to India became success in India and was super hit in India. These all locomotives were basically, except WDM1, is 16 cylinder 4 stroke locomotives with turbo superchargers. More than 3000 ALCO locomotives have been manufactured by Diesel Locomotive Works Varanasi so far. ALCO design were continued to be manufactured by Indian Railway till the introduction of GM locomotives, as I already told, in late 90s. Last in series of ALCO locomotive, WDM3D class, it was mixed locomotives, mixed for freight and passenger, AC/DC diesel electric locomotive, which is microprocessor controlled, was introduced on the Indian Railways in around 2003. This locomotive is equipped with 60-cylinder operated engine capable of producing 3300 HP under standard condition. Few locomotives of 3500 HP and 3600 HP, that was WDM3E and F, also tried out in ALCO design, but due to new GM locomotives, production of further ALCO locomotives was put on hold. So friends, this had been the journey of ALCO locomotives. We will discuss GM locomotive, that is also called EMD locomotive or HHP locomotive. We will discuss that separately. In this session, we will focus on ALCO locomotives only. Now let's know the basics of diesel engine working. A heat engine is a device which transforms the chemical energy of a fuel into thermal energy and uses this energy to produce mechanical work. As commonly known, there are two types of heat engines, that is external combustion engine and internal combustion engine. The examples of external combustion engine are coal or oil fired steam engines, and those of internal combustion engine are petrol, diesel and gas engine. In external combustion engine, coal or liquid fuel is burnt outside the cylinder. As we can see here, this coal is burnt, which is producing steam from water by heating it, and this steam is being used to move this piston, and hence this crankshaft is moving. So here the working fluid, that is steam, is different from the burning fluid, that is coal. So external combustion engine, both are separate and combustion is taking outside. In internal combustion engine, the fuel burns inside the cylinder. Here we can see this is a closed enclosure where mixture of air and fuel burns and produces heat energy, which forces this piston to move down, and by reciprocating movement of this piston, this crankshaft rotate and we get the output in terms of rotation of this crankshaft. Further, the internal combustion engines are again divided into two groups, that is spark ignition engine and compression ignition engine. Examples of spark ignition engine is petrol and gas engine, whereas example of compression ignition engine is diesel engine. Here we can see this is a spark ignition engine, this is compression ignition engine. Both are internal combustion engine. The basic purpose of an internal combustion engine is to develop power by burning fuel. Therefore, good performance of an engine is dependent on how quickly and completely the fuel can be burnt. This burning of hydrocarbon is called combustion, which is a chemical process accompanied by emission of light and heat. The petrol and gas engines are called a spark ignition engine, as electric spark, as we can see here, is used to burn mixture of air and fuel that is being supplied from the carburetor. The mixture of air and fuel is burnt by the ignited by this spark plug, and this produces the heat energy which causes the movement of this piston. The process of combustion in the compression ignition engine varies widely from the spark ignition engine. In case of diesel engine, only fuel is injected through this nozzle, not the mixture of air and fuel. Air is supplied beforehand and is compressed by this upward movement of piston, and so it is heated to a very high temperature. So when the fuel enters, it auto ignites. So there is no spark plug here. The fuel is auto ignited and it produces the heat energy which causes the movement of this piston. So the name compression ignition engine has been derived from the fact that air drawn in the suction stroke is compressed to such a degree in compression stroke that the heat generated due to compression goes much above the self-ignition or auto-ignition temperature of the fuel. So this is the major difference between a spark ignition engine and compression ignition engine. So why compression ignition engines were selected for locomotives? Few reasons are enumerated here. Higher thermal efficiency than a spark ignition engine due to higher compression ratio. So higher the compression ratio, higher will be the compression pressure and consequently higher the temperature. So basically, what is the compression ratio? Compression ratio is the ratio between total volume V1 plus V2 and the clearance volume, that is V2, when the piston reaches at the top dead center. So the clearance volume remains here. So basically it is the ratio of clearance volume to the total volume. So it also indicates the degree of compression of the trapped air. Diesel engine uses higher compression ratio than petrol engine because it is easier to compress pure air rather than mixture of fuel and air. Also, the lack of a spark plug in diesel engine means that compression ratio must increase the temperature of the air in the cylinder sufficiently high to ignite the diesel, because there is no spark plug and the fuel has to burn self. So the compression ratio must be high in diesel engine, and because compressing the mixture of and fuel will cause the problem of knocking, so there is a limit for compression ratio of spark ignition engine and is less around about 8 is to 1, whereas the compression ratio of compression ignition engine is 12 is to 1 and above. So since diesel engine is having higher compression ratio, so it have the better thermal efficiency. Secondly, it uses less expensive fuel. As we know, in India, diesel is slightly less costlier than the petrol. Third, diesel has higher specific gravity than petrol. In India, diesel and petrol are sold in terms of volume. So higher, because of higher specific gravity of diesel, we get more quantity, more you can weight of diesel than petrol. Also, running cost is less and longer life. But the most important point to choose compression ignition engines for locomotive is better fuel economy, particularly at part load. Because there was a survey in railways, and even you might have felt that most of the time our engines are running idle in idle condition or in at full rated speed at its notch. Around 50% of the time it is running in the idle condition. So the locomotive having better part load efficiency, that is at idle running condition, will be better for us. So diesel engine has better fuel economy, particularly at part load, and hence it is beneficial for us. Fuel safety, as we all know that we are consuming around 3 billion liters of diesel per year. So we are also storing that much amount of diesel in our railway consumer depots. So fuel safety is paramount, because had the petrol being the fuel, there could have been so many accidents, because petrol is highly vaporized and it can create the fume of fuel around the RCDs, railway consumer depots, and we all know that most of the RCDs are situated nearby busy stations and where the large populations area is there. So fuel safety has to be very much has been the very important factor. Also better suited for continuous running. Our locomotives is sometimes running continuously up to 40 days without shutting down. There have been many cases. So it is better suited for continuous running, because we have designed all the systems so robust, like cooling system, fuel system, lube oil cooling system, cooling water system. So it is designed to run for longer hours. And also, since we are just compressing air in the cylinder first, so it is better suited for supercharging. But the disadvantage is it's have heavier weight, noise and vibration, smoke and other. So we can see the advantages of choosing is much higher than the disadvantages. So we have gone for compression ignition engines for locomotives. In any heat engine, either 2-stroke or 4-stroke, these four processes have to happen to generate power. While in 4-stroke cycle engines, suction, compression, firing, exhaust are completed in 4 strokes of the piston or 2 revolutions of the crank. In 2-stroke engine, all these are completed in 2 strokes of the piston or 1 revolution of the crankshaft. Here we can see all the 4 processes. Suction or intake stroke, the suction or induction or intake, whatever we may call, of fresh air. fresh cool air must take place for the purpose of providing oxygen for combustion of fuel as also for the scavenging of burnt gas and taking away heat from the combustion chamber components. So the fresh air is supplied which is at the lesser temperature, and it is very much required to burn the fuel because it supplies oxygen. Without oxygen nothing can burn. So first it supplies oxygen, second it causes to expel the exhaust gas through the exhaust valves, and it also reduces the temperature of this combustion chamber because of its cool air. Then comes the compression stroke. Once the air is drawn in, the air inlet passage is closed, the trap air is compressed, this intake valve is closed, exhaust valve is closed, and it is being compressed by the upward movement of piston. The trapped air in the compressed due to upward movement of the piston. Once the air is highly compressed, it attains high temperature and pressure. So at this point, this air temperature reaches up to the ignition temperature of the diesel fuel. So at this stage, the fuel started injected from this injector. So there comes the power stroke. As soon as the fuel is injected, the firing takes place and peak pressure is achieved just after TDC. We call it TDC, top dead center. So the expansion takes place, which provides the movement of the piston downward and causing the rotation of the crankshaft. So this is the power stroke. So due to the rotation, again this piston is moving upward. Due to the inertia, it is moving after the power stroke, it is moving upward and it is expelling the exhaust gas in the exhaust stroke. All the fuel that is burnt out has to be expelled through this exhaust to the atmosphere so that the space can be made for accommodating fresh air for the next cycle of operation. So again the suction of air starts and it causes the expelling of remain exhaust gases. So again suction, then compression, fuel injection and power stroke, then exhaust. So this process is happening in 4 movement of piston from TDC to BDC. So this is the 4-stroke engine. Our ALCO locomotive is the 4-stroke engine, whereas General Motor supplied engine, GM type engine is 2-stroke engine. So in this session we will discuss only ALCO type. So we have this 4-stroke engine for ALCO engines. So now we discuss valve timing diagram of 4-stroke ALCO engine. This valve timing diagram is very much important for our ALCO engine because I want to tell you that we had earlier 2600 HP WDM2 loco and we had been able to improve its horsepower from 2600 HP to 3600 HP from the same engine block, same liner, the same dimension of liner piston. We have been able to increase the horsepower, and one of the reason to increase the horsepower from 2600 to 3600 is the improvement over the valve timing diagram. I will explain you what is the valve timing diagram, but it has a very significant role in improving the horsepower of our ALCO locomotive. As already stated, ALCO type of engine needs 4 stroke of piston, where stroke means movement of piston from bottom dead center to top dead center. So it needs 4 stroke for one suction, compression, power and exhaust, or 2 revolutions of the crankshaft, because one revolution of the crankshaft is equal to movement of piston from BDC to TDC and again TDC to the BDC. So in one movement from TDC to BDC, BDC to TDC, the crankshaft moves one revolution. So 2 revolutions are required to cover all these 4 cycles. Though superficially it appears that each of the stroke is distinctly for one major event, like movement of from BDC to TDC is the compression, from TDC to BDC is suction, from TDC to BDC is the power, and from BDC to TDC is the exhaust. But in actual practice, it is not quite so. These events sometimes overlap between 2 strokes for better performance. Like at the latter part of the exhaust stroke, as we can see here, this is intake movement from TDC to BDC. This is power stroke. This is compression stroke, and this is exhaust stroke. Ideally, the exhaust stroke should start from BDC to TDC, but it is made for larger duration. Ideally, intake stroke should be from TDC to BDC, but it has been become made larger. This is in terms of angle of crankshaft. One movement from the TDC to BDC covers 180 degree revolution of crankshaft. Further, one movement from BDC to TDC creates one complete revolution, that is 360 degree of the crankshaft. So it is in the terms of angle of movement of crankshaft. This is the power stroke. Ideally, it should be from TDC to BDC, but it is up to this point only. So similarly, exhaust, it should be ideally from BDC to TDC, but it is made for larger duration. So the reason behind is that to increase the power from the same configuration, what we have done, we have to appreciate that the fuel that enters in the cylinder takes some time to mix with the air and to auto ignite. Although this time is in the fraction of millisecond, but it requires some time. We have to give some time. So the fuel injection valve need to open slightly before, so that air and fuel can mix and burn. So by the time the piston reaches the TDC, it gets burned. So this is the principle behind giving some time. Similarly, I will discuss one by one why we have given extra time for each stroke. So these events sometimes overlap between 2 strokes for better performance. At the latter part of the exhaust stroke, when the piston is still moving upward, as we can see, this is the exhaust stroke, piston is moving upward. As we can see that before it reaches to TDC, here we have opened the inlet valve. So during this period, both exhaust valve and inlet valve are open. The inlet valve opens in our ALCO locomotive around 80.1 degree before TDC. So inlet valves open here. As we can see, here inlet valve opens and exhaust valve is also open. The supercharged air is at about higher pressure above the atmospheric pressure, reaches through the inlet valve and pushes out the burnt gas. This process continues up to 57 degree 57.7 degree after TDC when the exhaust valve closes. So the exhaust valve closes here and inlet is valve is also open. So in this period, this is the period of overlap where both inlet and exhaust valves are open. This is 57.77 degree, and this is 80.1 degree. Don't go into the details of dimension. I have just referred this figure. So during this period, both inlet and exhaust valves are purposefully been kept open. It causes the inlet valve forces the exhaust valve to come out from the exhaust valve. So it removes all the exhaust valves from the cylinder. It helps in scavenging. This is called a scavenging process. So for that purpose, for scavenging and for removing the exhaust gases with the inlet air pressure, this purposefully the inlet valve is opened before the exhaust valve is closed. So now when the exhaust valve is closed and piston continuing to move downwards, this means that in intake stroke started and more fresh air is sucked in through the inlet valve, but suction ideally it should be from TDC to BDC. We have already started a little bit earlier, and you can see here we are also closing it little bit later. It is continuous. It is around 35.4 degree after BDC when inlet valve closes. So this extra movement of the crank by this amount provides some more time for more air to find access in cylinder due to inertia effect. Thus, the first downward stroke is partially for scavenging and the rest for the suction. So during this period, scavenging is done where inlet gas is used to push out the exhaust gas, and this is after the exhaust valve is closed. At this point, this is complete suction because everything is closed, and it continues up to 35.4 degree after BDC when the piston is moving up. So actual compression starts from this point. Ideally, the compression should start from the BDC, but it starts from this point after 35.4 degree. So now the compression stroke starts subsequent to the air inlet valve closing at 35.4 degree after BDC. The air drawn in the cylinder gets trapped as the exhaust valve is also closed from before. Now the piston moving upward in second stroke, compression takes place right up to the TDC. So this is the compression stroke. But as I have already told that since the fuel has to mix with air and fuel has to uniformly distribute inside the cylinder, so physical mixing of fuel, and it also requires some time to burn chemically. So for that we have opened the inlet valve, we have opened the injector some time before the compression reaches the TDC, that is around 18.1 degree before the TDC. When the air is well compressed and heated up, combustion of the fuel compressed starts and peak pressure is achieved a little after TDC. So by the time piston moves little bit ahead of the TDC, the fuel is already mixed with the air and it starts burning. So we get the peak firing pressure at this point just after TDC. Thus the second stroke is partially suction and the rest compression, because from this point is used as a suction because inlet valve is closed, and from here the suction starts, and before the suction is completed we have injected some fuel 18.1 degree before 18.25 degree before TDC, and it terminates around 14.75 degree after the TDC. So peak firing is achieved here, and then this power stroke starts. In the third stroke, power stroke, high pressure developed in the combustion chamber forces the piston down and is called power stroke. But as we can see again that before complete, ideally power stroke should complete at BDC, but we can see here that a little before the end of the stroke, that is around 57.77 degree, the exhaust valves are opened. So as the exhaust valves are opened, the exhaust gas starts going out. The burnt gas and the some pressure find outlet through the exhaust valves, and the residual pressure and energy, which was of not much subsequence in developing power in the cylinders, helps in driving turbocharger, and extra time with exhaust valves open avoids back pressure in the exhaust stroke. So since the exhaust gas started coming out early, so we have the reduced pressure inside the cylinder. So it helps in movement of the piston from the again BDC to TDC as the pressure is reduced, and the exhaust continues up to the TDC plus some angle to completely evacuate the cylinder from the exhaust gases. So after the piston passes the BDC, the fourth stroke starts and physically pushes the burnt gas out. But at a point 81.1 degree before the TDC, the inlet valves again opens with exhaust valve already in open condition. At this stage, the pressure of the exhaust valves has come down considerably, and the pressurized inlet air scavenges the burnt gas. This continues till 57.7 degrees. So this period where both in which we both inlet and exhaust valve is opened. So the fourth stroke is mainly exhaust stroke, but the later part of it is used for scavenging when both inlet and exhaust valves are in open condition. Basically, scavenging is a process of replacing the exhaust gas in the cylinder with the fresh air for the next cycle. If scavenging is complete, the remaining exhaust gases can cause improper combustion for the next cycle, leading to reduced power output. So scavenging has a significant effect on the efficiency of engine, and I have already told you that we have increased the horsepower from 2600 to 3600. So scavenging had a very great role to play. In conventional engine, this valve overlap when both inlet and exhaust are open for scavenging. Earlier it was 123 degree, but it was modified to 140 degree in our updated engine. From the above, it is clear that the four stroke of this type of engine covers all the four requisite events of compression ignition engines, and we have given some extra time for each movement, and we have curtailed times for compression and power stroke, but we have given extra time for intake and exhaust for getting more power. So this is the valve timing diagram, we call it. The valve timing has been indicated in terms of the angle of movement of crankshaft for better understanding. So once again, let me erase it and explain. So again, I'm explaining it. This is the intake stroke as written. This is the power stroke. This is exhaust stroke. This is compression stroke. Ideally, every stroke should be of 80 degree from TDC to BDC or either BDC to TDC. But for inlet and exhaust, we have given extra time, and for power and compression stroke, we have reduced the time. And this is the period which is called scavenging period, where both inlet and exhaust valves are open simultaneously. It is basically due for scavenging, in which the inlet air pressure kicks out the exhaust gas from the exhaust valve, so it evacuates the remaining burnt gases in the cylinder, so more air can be accommodated inside the cylinder. And since we have improved the angle from 123 degree to 140 degree, so we have improved the scavenging in our operated engine, and it is one of the factor which has caused increase in horsepower of our engine. From the same configuration, the block that was used in 1960s are still being used in WDM 3D loco with slight modifications, but dimensionally it is same. So this is the valve timing diagram, very important. Let us now discuss the importance of supercharging by turbo supercharger and the use of aftercooler. So this is about the our liner and piston. So here the exhaust manifold exhausts are coming out. Here we can see the turbine. This is the compressor and turbine. This is the part of turbo supercharger. The engine is equipped with a turbo supercharger to efficiently provide the air needed for combustion and scavenging. The turbocharger provides air supply in larger quantity during engine operation. The turbocharger utilizes the heat energy in the exhaust. The exhaust energy is coming and it drives the turbine. The turbine then drives a centrifugal blower. This is the air intake. So as the exhaust valves rotates this turbine blade, since the blower is mounted on the same axle, so this starts moving and it compresses the air. The air from the centrifugal blower is raised to a higher pressure and likewise to a higher temperature. It is desirable to reduce the temperature to increase its density before it enters the air V channel for supply to the cylinders. So as the air is compressed, but it also gets higher temperature. So as we cool the air, it will increase its density. So more air can be taken into the cylinders. So there is a after cooler. So this cools the air, the heated air and compressed air. So what does a turbocharger and aftercooler do? The turbocharger is raising the charged air pressure to increase its density and hence more air is supplied, and aftercooler reduces the compressed charged air temperature further to increase its density. More density of air means more quantity of air in the given volume of combustion chamber. So accordingly, more fuel can be burnt and more energy can be produced from the same given volume of combustion chamber. Had this turbocharger and aftercooler not been there, then the normal air would have entered into the cylinder at an atmospheric pressure, but due to the turbo supercharger we are increasing the pressure of the air to a higher level, and also we are reducing the temperature of intake air by use of this aftercooler. Similarly, high level of scavenging will cause the very little amount of exhaust gas entrapped inside the combustion chamber. So more quantity of charged air will be filled in this air. So one side we have scavenging because of this intake air pressure, because we are using pressurized air to evacuate these exhaust gases, the scavenging and the entry of pressurized air. So we in this given volume we have increased the volume of supply for air. So more air means more fuel can be burnt inside the cylinder and we can increase the power from the same volume of the cylinder. So this is how we have been able to achieve higher horsepower from the same dimension of engine. So the scavenging and turbo supercharger and aftercooler has played a significant role in improving the horsepower of the engine. So this is the role of turbo supercharger and aftercooler that we have discussed now. Now we discuss filing order. This is also very important. In case of 4-stroke cycle engine, there is only one power stroke in the 4 strokes of piston or every 2 revolution of the crankshaft. To increase the power output and to make it smoother, multi-cylinder engines are used in which the firing stroke on different cylinders are suitably placed in relation to the crank angle so that during the revolution of the crankshaft, firing of the cylinders takes place one by one at regular interval. The firing order is used to prevent damage arising from vibrations set up in the crankshaft. The sequence of firing is so arranged that the vibration tend to cancel out as far as possible. So as already we have discussed, we have one power stroke in 2 revolution of the crankshaft. So during the power stroke, the cylinder gets high thrust, so vibration will be more. So how can we nullify or minimize this vibration? So at a time, suppose from one direction the power stroke is happening, simultaneously from the other direction, if from opposite direction, if same power stroke happens, then it can nullify the vibration. So we have arranged the power strokes of different cylinders so that the overall vibration should be minimized. Since in ALCO locomotives we have V-type cylinders and total 16 number of cylinders, so we have arranged the firing order in such a manner to reduce the overall vibration of the power pack. So here we can see for our railway standard engine, the following firing order has been prescribed for ALCO locomotives: 1R, 1L, 4R, 4L, 1, 4, 7, 6, 8, 5, 2, 3. Here R and L refers to right and left, and 1, 4, 7, 6, 8, 1, 2, 3, 4, 5, 6, 8 is the row of cylinders. We have 16 cylinders, 2 cylinder in a row in V configuration. So 1, 2, 2, 4, 3, 6, 4, 8, 9, 10, 11, 12, 13, 14, 15, 16. This in 8 row we have 16 cylinders. So one right and one left is firing simultaneously. Then after 4R and 4L, then after this 7R and 7L, then after this 6R and 6L, then after that 8R and 8L, then after that 5R and 5L, then that 2R, 2L, and last 3R, 3L. Again, this cycle is repeated. In this manner, the power strokes takes place in our ALCO locomotives power pack. Here, one is counted from the free end. I will talk in our power pack config when we discuss power pack. Free end, from free end we count the number of cylinders. So on the free end we have number 1 cylinder, number 2 cylinder. From that, from number 1, 2, 3, 4, 5, 6, 7, 8, and for right and left, the convention we stand in the engine compartment, in driver compartment, and look towards the engine, and our right is engine right, our left is engine left. This type of configuration we use generally. So now coming to our locomotives, I am giving the brief idea before we are going to discuss the different components of power pack. We have ALCO and HHP, that is the GM engine, that is GM made. This is ALCO. In ALCO we have WDM2, WDM3A, WDM3D, WDG3A, WDS6R. This is shunting locomotive. These locos are majorly used in our system. There are other variants also, but these are the major. In HHP, that we will discuss in HHP class, WDG4, WDP4, WDG4D, and WDP4D. So population of total diesel locomotives is around 6,300, including both broad gauge and meter gauge. Net holding of broad gauge locomotives is 5,578 as on 1st of April 2020. HHP loco is nearly 2,500, out of this 5,578. Number of diesel sets for broad gauge diesel loco is 42, and we are also doing periodic overhauling of diesel locomotives at 6 locations: Jamalpur, Parel, Ajmer, Kharagpur, GOC, Charbagh, Lucknow. So this is the brief introduction about the locomotives of Indian Railways. Here I have done some comparison which is shown here. These two are HHP locomotives, WDP4D passenger, WDG4D goods loco. This is the ALCO locomotive passenger, WDM3A or oblique WDM3D, and this is goods loco of ALCO type, WDG3A. So ALCO locomotive having 3100 HP horsepower or 3300 horsepower, but HHP we have higher horsepower of 4500. In strokes, HHP engines or GM engines are 2-stroke, but ALCO engines are of 4-stroke. Compression ratio used in ALCO we have 11.75. In HHP we have 16:1. Transmission we have AC transmission in HHP loco, but in ALCO we have AC-DC transmission. This is the gear ratio at the wheel. Axle we have the bull gear on the axle and pinion on the traction motor. We will discuss in detail later on. So this is the ratio of bull gear to pinion. We can see here that gear ratio is more in goods locomotive and less in passenger locomotives. This is intentionally been designed to, because higher torque is required in goods locomotive and higher speed is required in passenger service locomotives from the same horsepower. Maximum RPM, revolution per minute at the full rated 8th notch, 950 is the RPM in HHP engine. In ALCO we have 1050 RPM. Similarly, this is the lube oil tank capacity, since HHP locomotives are bigger and has higher capacity for lube oils, and ALCO locomotives have lesser capacity of lube oil of 1025 liters. Axle load, this is the axle load. Passengers passenger loco axle load is little bit less than the goods. ALCO is little bit lighter than the HHP. Tractive effort very significant. We will discuss it later. That tractive effort of HHP locomotive is much higher, 54 ton. That's why it is being preferred. And our ALCO locomotive tractive effort is 40.5 ton. In passenger it is not of much significance, but in goods it has a very much significance. Similarly, fuel tank capacity in these locomotives of almost equal, and maximum speed here mentioned here. For passenger we have higher speed and goods we have 100 kmph. So this is the basic some data for comparison of HHP and ALCO locomotives. Since we are beginning into the power pack of HHP, ALCO and HHP, so before that we have compared some data. Now, so far we have discussed in this video brief history of diesel locomotives in Indian Railways, basics of diesel engine working, types of heat engine, why CR engines for locomotives, effect of higher compression ratio and scavenging, cycle of operation of CI engine, valve timing diagram, firing order, and lastly the types of locomotives in Indian Railways and their basic parameters. So friends, this all in this video. In my next video we will discuss the different components of power pack of ALCO locomotives, and further in more videos we will discuss HHP locomotives. So as of now this is for this video. So I hope you have enjoyed my video. Thank you for have patience listening. Thank you, dear friends.